In the first two lectures, we have derived finite elements through the Poisson's equation with very simple zero-Dirichlet boundary condition. In the last lecture, we took a very deep dive into the mathematical foundation of finite elements, discussing how do you convert a partial differential equation into its weak form, how to treat the boundary conditions of the partial differential equations inside the weak form. Right? We discussed the natural boundary conditions, which means we can incorporate the boundary condition into the bilinear form, into the bilinear functional and the linear functional of the weak form. If that fails, we can resort to an essential boundary condition, which means we restrict the space on which we allow the solution and we allow the test function, so that we basically brute force it to satisfy the boundary condition. So these are the two alternatives we used to enforce boundary conditions. Today we are going to discuss, now we have the weak form, how can we go to finite element with the weak form, which is pretty much trivial, you're going to see. All we are doing in finite element is basically deriving the weak form. And once you have a weak form and you choose the space in which you allow your solution and you allow your test function to be, then finite element basically follows. Okay. So weak form and finite element are basically coupled together. So the weak form, let me write it in the most in a general way, is that we have a bilinear form that operates on the solution U and the test function V. This has to be equal to a linear functional that is operated only on the test function V. Okay, and this has to be true for any V within a certain space. So this X is a vector space, or vector space of functions. Okay, this has to be satisfied by a function U within another XB, where XB is an affine space. By affine space, we usually mean a space of a vector space with particular restrictions on the boundary. It's a subset of all elements in a bigger vector space that satisfies a particular type of boundary condition. What do we call them? What do we call the type of boundary condition we enforce by restricting the space? Essential boundary condition. What is the other type of boundary condition? Natural boundary condition, which we don't restrict the space but modify the linear and bilinear functionals to achieve that boundary condition. Okay. In finite element, you're going to see that if we enforce a essential boundary condition, the boundary condition is usually satisfied exactly because that's how we enforce them. If you look at a natural boundary condition, the boundary condition is satisfied up to the discretization error. So it is not going to be satisfied to 10 to the minus 18. It is going to be satisfied to like 10 to the minus 5, 10 to the minus 6, depending on how fine your grid is. Alright. Okay, so this is the general weak form. And to go from this to finite element, as I said, is almost trivial. So this X is an infinite dimensional space, but we are going to choose a particular XH that is a subset of this X. It's a subspace of this X. Okay, and we are also going to choose a XHB that is a subspace of this XB. Both of these should be finite dimensional, and they should have the same dimension. How do you determine a dimension of a vector space? How do you decide a space is 100 dimensional versus 200 dimensional? How many bases? What is the size of the basis of that space determines the dimension of that space. A two-dimensional space is two-dimensional because it has two bases. If you pick any two directions that is not collinear, then any element of that two-dimensional space can be expressed as a linear combination of that two vectors. A three-dimensional space, there are three elements. As long as they don't lie in a plane, that is the basis of that three-dimensional space. So if you can find a set of functions that forms a basis of the space, then the number of these elements, the size of the basis, determines the dimension of the space. What if you can't find a set of bases, finite set of bases? That means it's an infinite dimensional space. That's right. That's right. For example, L2, H1, the stuff we are talking about last time, all of them are infinite dimensional spaces. That means in finite element, we need to choose a smaller space, a subspace of these H1 or L2 spaces in order for us to apply finite difference. So after we choose this, we keep exactly the same bilinear form. We don't change the bilinear functional, we don't change the linear functional. They stay exactly the same. What we change is basically, instead of having U to be in the bigger space, we have our UH to be within the smaller space within XHB, and VH to also be in the smaller space, but we keep the same L and same B. And this has to be true for any VH in XH. Okay, that's our finite element. So the weak form to finite element is a very, very simple step, just choosing the subspaces. Different subspace gives you different finite element discretizations. Remember in our first class we discussed finite elements. If we choose piecewise linear and continuous functions, that is one choice of space. If we just choose piecewise linear but perhaps discontinuous elements, it's a different type of finite element scheme. But once you choose these two spaces, we have a finite element scheme. Okay, that is because in order for this equation to be true for any VH, right? Let me just different color. In order for this to be true for any VH, we only need to enforce this equation for the basis of this space XH. So we only need the B of UH with phi j to be true for j equal to 1 to n, which is the dimension of XH, and phi 1 etc. to phi n is a basis of XH. Alright. And also UH. So now we have a finite number of equations. Do we also have finite number of variables? Finite number of variables to solve for? We have a UH that is now no longer in the infinite dimensional space, but in a finite dimensional space. Right? It is not a vector space, but it is what we call an affine space. Affine space, which means it is going to be a constant plus a linear combination of bases. So that UH, where UH is equal to let's say UH naught, which is a constant, plus a linear combination I goes from 1 to n, AI times, maybe I have a different set of bases psi j, right? But then I can always have a map, have a unique map, have a bijection between an element in XHB and a set of real numbers, A1, A2, A3 to AN. If I have a UH, I can uniquely derive the set of numbers, right? Of course, that's given a set of bases psi j, psi I, sorry. This is I, right? Given a set of bases. If I have a UH, I can get a bunch of A's. If I have a bunch of A's, I can get the unique UH. So basically, I have n equations and n variables, and these are the variables, and these are the n equations. After I solve for the A's, I have a solution. Okay, any questions? This is basically a one slide that gives you a finite element algorithm if you have the weak form. So all you need to do is pick a weak form, derive a weak form actually, and pick the function spaces. Pick the function space for the solution, which we call trial space, and pick a function space for the test functions, for the V's, which we call test space. Any questions on this? Okay, so now we have the general formulation. What we're going to be talking about is some nuts and bolts, the details of how to implement them for different type of equations. First, for steady state equations, unsteady equations, we're also going to talk a little bit on how to choose a different space than what we have been working on so far. Okay.